Here I'm using WaveMason to simulate the 3 transmission lines into a resistor. This time the first transmission line is 50 ohms and it's 2 wavelengths long at 1 gigahertz. The second is a 70.7 ohm transmission line, and it's also 2 wavelengths long at 1 gigahertz. But this time the length is a little bit shorter physically, and that's because the wave is going to travel slower through this medium. And the third line is 100 ohms, and the wave travels even slower through this medium, so it's shorter still. And then I have a 100 ohm resistor, so there should be no mismatch between these two. I'm going to inject my Gaussian pulse, and we're going to see a little bit of reflection because we're going from low impedance to high impedance. We're not going to change sign off of the reflection. And we get another reflection, and the impedance, the voltage actually gets higher as you go from the lower impedance to the high impedance. And that has to do with the ratio of the voltage and the current and power being conserved. Now, when we took a look at the voltage wave that's returned back towards the source, we see a lot more structure now, that we have a little bit of waves rattling back and forth. And what's happening is we have places where the energy going back to the source is destructively interfering with all the energy that's rattling around from the first bounce and the second bounce. So at certain places where the electrical length is just right, we end up with these nulls, less energy to no energy going back to the source. And now I'm going to inject my DC pulse, just so we can see what happens to a DC signal when we have mismatches through the line. And we can see that the voltage changes. It actually is getting a little bit higher as we're going from this lower impedance to this higher impedance mismatch.